Hello community! Today we have a look at some brand new AI models and special applications. So end of October 2024, we have here from Department of Physics from Yonsei University here in Korea, some beautiful new publication about a neural Hamiltonian. Can AI understand Hamiltonian mechanics? So we are now working here at the intersection of artificial intelligence and theoretical physics, and finally we have a real application of AI. So what we will do, we will be reformulating the Hamiltonian equation, this fundamental equation in classical mechanics, as an operator learning problem for AI. So we will aim to develop here new efficient computational methodologies for simulating and analyzing Hamiltonian systems in theoretical physics. And what these two authors showed here from Korea, that the study bridges here a gap between the classical mechanics and the modern machine learning, demonstrating that operator machine learning can effectively model complex physical system. So finally, maybe AI is able to understand the real-world complex physical system, and we do this here with the implementation of operator neural networks in physics. Here we go. What is so beautiful? We have a new mathematical framework that treats now the Hamiltonian equation in theoretical physics as an operator mapping from potential function to time-dependent positions and momentum functions. So this approach bypasses now our traditional methodology to solve differential equations explicitly, OCA4. So the algorithm for generating here the potential functions is now here. We have a new combination of Gaussian random fields, GRFs, with cubic B-Splines. And this methodology we use to generate smooth and bounded potential functions that are physically, in our simple demonstration, plausible and satisfy the mathematical preconditions necessary for the Hamiltonian equation to be valid. We will have two novel neural network architecture. The first one is called VaRONet and simply adapts here a Variational LSTM, a long short-term memory from the 100 years ago in artificial intelligence sequence-to-sequence model for the operator learning. MambONet, you are familiar, I have several Mamba videos on my channel. MambONet leverages here the Mamba model to efficiently process here the temporal dynamics of the Hamiltonian physics, theoretical physics. Now, these new systems are not just reinvented yet, but they are based here on a lot of research done in the last years. So this new architecture aims to capture the complex relationship inherent in the Hamiltonian dynamics more effectively than our models that you might know, DeepONet and TraONet. If not from a green grasshoppers, here before here the transformer hype started here at the beginning of 2020, we had a beautiful publication by here, Division of Applied Mathematics in Brown University and Academy of Mathematics and Science from the Chinese Academy of Science. DeepONet, learning nonlinear operators for identifying differential equation based on the universal approximation theorem of operators. This is a base study you have to know. And then I would personally recommend you this here from October 2021. We are here, University of Pennsylvania, Applied Mathematics. Yeah, all of them, great. And they talk about analyzing the dynamics of deep operator network, these DeepONets, through the lens of a neural tangent kernel theory. And I have two videos here on NTK theory if you're interested, or wherever sources that you have access to. Now, what I now personally need to do, I had to fresh up my knowledge because this here is a source that I found I will use now this weekend. Maybe I can recommend it to you from end of December 2023, Department of Applied Mathematics from Cambridge University and Department of Mathematics from Cornell University, a mathematical guide to operator learning. I found this the best resource to learn here, operator learning. Aims to discover properties of an underlying dynamical physical system or partial differential equation from the data. And they represent here a step-by-step guide to operator learning. And I found this highly helpful. I just scanned it through. It will take me probably a complete afternoon to read it, to understand it. But I think this is what maybe we both need. Within this paper, you will find here the most important theorem. Maybe you're familiar with it, the universal approximation theory of operators. Suppose that sigma is a continuous non-polynomial function, x is a Banach space, we have k1 and k2, two compact cycles in x, where v is a compact cycle in c, and g is a nonlinear continuous operator which maps v to c. Then there's a positive integer and some constant such that this expression here is smaller than an epsilon and it holds for all u element v and all y element k2. Not trivial, I will need time, but based on this theorem 1, they build now their architecture for their very rudimentary AI system, for the classical DeepONet system. And as you can see here, we have a stacked DeepONet based on theorem 1, which has a one trunk network and a p-stack branch network. This is here in C, and then we have an unstacked DeepONet where we have one trunk network and one branch network. More older explanation is done here in the scientific literature, but we have to focus now on the latest in operator learning framework. Operator learning extends now the neural network's universal approximation capabilities from function to operators mapping between function spaces. So we increase the complexity on one step. As I showed you, DeepONet architecture, branch and trunk network serves here as a foundational model for operator learning in the study from the 2020-2021. And by treating the Hamiltonian equation as an operator problem, the study leverages here the framework to predict trajectories without solving differential equations explicitly. This is beautiful. So now let's talk about here the generation of our potential functions. Sorry. So the combination here of our GRFs and our cubic B-splines ensure that the generated potentials are smooth, satisfying here a continuity function and bounded within the compact domain, which we need to have as a boundary condition here, as a starting condition for our Hamiltonian equation. And this approach addresses here the challenges of generating training data that is both diverse and physically meaningful, crucial for training operator learning models. Well, of course, I ask here my little ChatGPT O1 preview to explain here why we need a Gaussian random field and a B-spline. And it gets here, what is this? What is a cubic B-spline? Continue satisfying the smoothness requirement of the Hamiltonian equation. Generate random values at the control points using here the Gaussian random fields, and then normalize this and adjust these values to ensure that the potential is bounded. And then we use here the cubic B-splines to interpolate between this exact control points, resulting in a smooth potential function. Mathematical formulation of this is here with the B-spline base function of degree p. Now these two new architectures, these two new AI models that I showed you, VaROnet, let's have a look at this. They incorporate here different aspects of our set of AI models, and they incorporate here a variational autoencoder with an LSTM, a long short-term memory network from the 100 years ago. What it does, it captures here the stochastic nature and the sequential dependencies of the Hamiltonian system that we need. So it also uses here, remember, we have position and momentum as our input parameters to the Hamiltonian system equation. It uses now dual decoders exactly for this position, thereby improving here the spatialization and the accuracy compared to our classical methodologies. Now the second, the Mamba system, the MambONet system, now the second new AI model here is even more interesting because, of course, it is based here and integrates here the Mamba model, see my videos on this channel, which effectively handles here the long-range dependencies without the quadratic complexity of our self-attention mechanism, but also combines the Mamba blocks and the branch networks with a transformer decoder in the trunk network. So we combine here, if you want, the best of two worlds, but we have to be careful what element we use for what functionality in our new AI model. So Mamba blocks go to the branch network and the transformer decoder go to the trunk network. Therefore, we need really to understand theorem 1 that I just showed you at the beginning of this video. And this demonstrates enhanced scalability and performance, especially with larger dataset. I will show you the results of the larger dataset in a second. Here we go. They did it here with two test datasets. They had a standard dataset and then they had an extended dataset that is 10 times as large as the standard dataset to have a feeling for the scaling parameter. So MambONet outperformed our classical RK4 in terms of mean total loss, indicating here higher accuracy. VaROnet also showed competitive performance, almost closely matching here our traditional RK4. This means DeepONet, the classical, of course, like suggesting limitation and capturing here the complex Hamiltonian dynamics without further architectural enhancement like we have done in MambONet or VaRONet. Yeah, from my green grasshoppers, okay, what I'm talking about Runge-Kutta methods here, solving ordinary differential equation, beautiful numerical methodologies. We have here the Euler method. And then if you want to improve here, since the Euler method is only a first order accurate, can be insufficient for many practical purposes due to its low accuracy and stability issues, we have Runge-Kutta, those are two German mathematicians, improved about the Euler methodology, I think in 100 years ago, more than 100 years ago, right? Please check it, by taking multiple evaluations of the derivative with each step to achieve a higher order accuracy. And we have here, normally we go with accuracy of 4, so an RK4. Now, the results of the extended data set was 10 times as big. All models, but particularly here our new two MambONet and TraONet, benefit from this increased training data like our classical transformer architecture. And it was here MambONet that showed remarkable improvement, so significantly surpassing here our Runge-Kutta 4 or K4 and other models in accuracy. We're going to talk about the computational timescale in a second. So those results now from the extended dataset, if you have a real huge dataset that we need, highlight the scalability of the proposed architecture, which is check, and the ability to leverage larger datasets effectively. So this is nice if we have a real complex mathematical function and maybe we have different system parameters. Oh yeah. Testing now on the known potential and the potential function here for harmonic oscillator or Morse potential demonstrated here the Morse practical applicability, and especially again MambONet here accurately. So this combination here of solid state space here and transformer architecture accurately predicted the trajectories for potential outside of the training distribution, showcasing here a strong generalization capability, which is really interesting to understand a little bit more in detail. Of course, here the mirrored threefold potential is kind of a challenging test case. And computational efficiency, this is interesting here. While the neural network models did not consistently outperform here Runge-Kutta 4 in the computation time, the MambONet's efficiency was comparable. So now this shows you, okay, we're just at the beginning. This is just the second step maybe here in developing new AI models, because our classical models to solve differential equation, RK4 for example, are still competitive, especially if you look here at the time invested. But it seems that MambONet has the edge if you evaluate here the accuracy. So you have here this famous trade-off between the computational speed, the time, and the actual accuracy of our new AI models. And it seems that this favors here the proposed new model, especially a MambONet here in scenarios where we really have to have a clear and beautiful accuracy of our systems. Taking a step back, we can now say, hey, the ability to predict here a system dynamics without solving here our classical differential equation explicitly, this could really, and I really mean it, revolutionize here the computational physics and the engineering simulations here from material science to computer science. This would be a complete new way. But the complexity that we have here, this combination of Mamba and linear projectors and dual encoders and decoder structure and transformer architecture and mixed layer and filtering, this is not as easy as it might seem here at the first glance. Yeah. And then I just wanted to show you here where are we with the performance here of our best system of OpenAI's O1 preview. So I give it here the complete study and I give it here 3-4 additional studies for the mathematics. And this is what I got back. And I want to show you this because I'm now a little bit jealous. So it understands perfectly here the universal approximation theory for neural networks and that extension here to the operator level. Beautiful. Deep operator networks, this DeepONet, yeah, I explained it here. It understands here the basic functionality. It pretends to copy here from the original literature, and then here the universal approximation here for the operators, and here our universal approximation. As I showed you, this is our master theorem. One, beautiful, so I got it. And then I tried to apply it here into Hamiltonian mechanics and the operator formulation that we have now. I understood here the phase space and symplectic structure, reformulating here the Hamiltonian equation as an operator equation. And defined here the gradient and everything and the mapping between the function spaces. And at this moment I thought, this looks good, no? I mean, just looking at it, saying, yeah, it sounds good. I have not looked at each and every single notation, but in general, yeah, this is it, how we do explain it. This is what is here really the case, no? But then I thought, but wait, this is just here a reproduction from the original papers, no? This is just what lines the system copies out of the original paper. And I thought, okay, but what is missing, no? Because I said, this happened in 11 seconds, you know? And I studied, I don't know, 120 years. So I said, what it does not understand here, our current AI system, is why these distributions, why these formulas are there, why this is valid, you know? What is the idea behind these simple lines? This is just a line of symbols for the OpenAI systems. But behind this, there's a theorem, there's something that we want to understand. Here, the process of solving Hamiltonian equation, you know, what if you really want to do it to be precise with a mathematical background, you have to show all of these different steps and that you can do it. This is a valid expression and that the mapping above is well defined and injective and whatever you need, you know. All of this deeper understanding is completely missing. The AI is just taking here in 4, 5, 10 documents and then generating here kind of a summary just of the symbols. And when I tried really to question here specific parts of the theorems that was not part, of course, of the input that I provided here, of course it failed. So, okay, but you know, this was really where I thought, hey, AI is really making steps forward. So you could be, or I could be tricked into thinking that the system really understands what it is here replicating from its copied material. But yeah, you just have to pinpoint down on a deeper level and you see that the AI system breaks apart because it has no idea what it's doing. But yeah, I think on my side too, if you go deeper and deeper on one level, I will just say, sorry, I don't get it. So interesting. What is also impressive here, I ask here ChatGPT-o1 preview here to explain VaROnet. And after 5 seconds, it came up here, architecture overview, mathematical details for the encoding, variational sampling here and decoding with LSTM. Yeah, beautiful. It combines the loss function. So it could extract all of this from the literature within seconds, you know. And I need, I don't know, 1 hour, 2 hours to read a paper. So the speed is impressive, and it's really, sometimes I think that the system would understand because it looks logic. It is a feeling that you would say, yeah, this is the way to do it. No? Yeah, but it just copied certain passages out of this. No? And also MambONet, look, 1, 2, mathematical detail, block, networking process, team working process, yeah, loss function defined. It seems impressive. Okay, but look, but this is what I know about VaROnet. No, I just know that it captures here the stochastic aspects and the uncertainty. It leverages some sequential dependencies via our old LSTM, and it has a dual decoder for allowing the specialization here in our momentum and our impulse input parameter. This is all I know about VaROnet. MambONet, also just 3 points. No? It effectively handles here the long sequences. It has not the squared complexity. It reduces here the complexity and demonstrates scalability with the large data set. This is all I know about it. No? So, yeah, OpenAI o1 preview. You have really a speed reading, but maybe not yet the understanding. Yeah? And me too, by the way. I'm lacking. I need a complete day maybe to understand this. So what I just wanted to, why I chosen this particular paper for today's video. The Hamiltonian formalism, especially here if you start here very young here in physics and mathematics here, it introduces here a fundamental symmetry between the position and the momentum variables, providing here a deeper insight into the structure of the phase space here that we're working with in theoretical physics. And a key feature here of the Hamiltonian formulation, especially here in the classical formulation, is its symplectic structure, which naturally preserves the certain geometric properties of the phase space. And this structure is intimately connected to the Liouville theorem, ensuring that this phase space volume conversation is happening. And this is a fundamental principle in statistical mechanics. So if you take a step back and you think about this, you discover that there's another path forward, no? Because one of the most profound aspects of the Hamiltonian equation is the connection to the quantum mechanical interpretation. And the Hamilton formalism, my goodness, provides here a more direct route to quantum theory through the correspondence here between the Poisson brackets and the quantum commutators. But this needs to be continued in a different video. But you see exactly, this maybe could lead us here in a completely unexpected way to apply here not just the knowledge of EI, the computation, to the Hamiltonian equation, but bridge this gap here over to quantum mechanics. I don't know if this is possible, but I think this study opens up here a beautiful new pathway forward. And if we could do this, if we could take here simply what we know about the Poisson brackets and the quantum commutators, and we could make the AI understand and perform this for us without the classical solving the differential equation, this sounds absolutely fascinating. Okay, I think this is it for today. To be continued. Yes, we will move to quantum mechanics with AI in sometimes, maybe beginning of next year, quantum commutators. But yeah, maybe you give me a feedback if you kind of like a little bit more advanced AI. You know, I was not talking about the latest public relations shout out from a new model from, I don't know, OpenAI or Microsoft or Google. We were not talking about real world applications where AI is really helpful, where AI itself is kind of a tool that we do not have to have this calculation of our differential equation, but we can use AI as an advanced tool to solve different problems we couldn't solve before. And I think this is, for me, the absolute fascinating aspect of AI. I hope you had a little bit of fun. It would be great to see you in my next video.